In this video, I'm going to talk about controllability and observability. How do you define it and how do you find whether that system or model is controllable or observable? So some basic definitions. Transfer function. What is a transfer function? It's a relation between output and input of a particular system. So here is the definition. In order to develop the transfer function, we have to assume initial conditions are 0, but initial conditions need not to be 0. So transfer function is nothing but output over input, assuming initial conditions 0. But in reality, initial conditions need not to be 0. So here, this transfer function, it's a mathematical equation representing in S domain, which is 1 over s square plus s plus 1. Okay, so this is a mathematical equation in S domain. Okay, here the denominator is called characteristic polynomial. When you make it equal to 0, it's characteristic polynomial equation. Now it has two poles. The order of the system is 2, so it has two poles. That indicates it has two state variables. Okay, so when I convert this into time domain, you can write this as y double dot plus y dot plus y equal to u. This is a same mathematical model in time domain. So depending upon the order of the model, we can find number of state variables, as I said. So here this mathematical model has second order system. I mean, we care about the denominator, not the numerator. Numerator represents the zeros, denominator represents the poles. So it has order of the denominator is 2, so it has two poles or two state variables. Now state variables are defined mathematically and are usually selected to satisfy mathematical condition. So I'm talking about this point here. State variables are defined mathematically and are usually selected to satisfy mathematical conditions. So when we select the state variables, say for example, you're designing a car, okay, your car. So in the dashboard, you want to see how fast you're going. You want to see how hot your engine is so that you can, I mean, if it's getting hotter, you can stop it somewhere. And you want to see the fuel level. Those are the important things. Now, instead of showing you the fuel level, if I show you the air level in the tank, that means, half of the tank is filled with, I mean, whenever the fuel is going out, the empty space is going to fill with air. So then you have to do some other calculations to find out the fuel level. Okay, so to avoid that, you have to find the right state variable. When it comes to the electrical circuits, we always choose current passing through the inductor as one state variable and voltage across capacitor as another state variable. So those are the two state variables. So if a circuit has three energy storage elements, two capacitors and one inductor, so two state variables are the voltages, voltage across each capacitor, and another state variable is current passing through the inductor. Okay, the next point, the selected variables may or may not provide an effective representation of the physical system. So similar to what I discussed, some variables may not represent exactly what you need. Two quantities we need to ask ourselves to find whether the model is controllable or observable or not. The first question is, are the selected variables well connected to the input? In other words, when the input changes, will all state variables be affected? Okay. If the answer is yes, then the model is controllable. Okay, so the first thing is, so here is the question 1, are the selected variables well connected to the input? In other words, when the input changes, will all state variables be affected? So if the answer is yes, then the model is controllable. The second question is, state variables are well connected, or all state variables are well connected to the output. In other words, when each state variable changes, will the output be affected? If the answer is yes, then the model is observable. So that's how we define whether the model is controllable or observable or not. So again, controllability comes with the changing in the input, uh, and observability comes with the output. Now the important points, mathematical points, are controllability will depends upon the A and B matrices. Observability will depends upon the A and C matrices. Now here is a simple example. X dot, here you have three state variables. It's a 3 by 3 matrix, you can see clearly. So here he's asking you to find the model is controllable or not, also find the system is observable or not. So here x dot, x1 dot equal to minus 3x1 plus u, okay, x2 dot equal to minus 4x minus 4x2, x3 dot equal to minus 5x3 plus u. Here if you look at here, x1 dot, okay, this variable is depending upon the input. Okay, so as long as our when controllability definition is, or when input changes, will all state variables be affected. So here I can clearly see for sure if my u is changed here, x1 is going to be affected. U changed, then my x3 is also affected. How about x2? Now x2 is not any one of these other two equations. X2 is not involved in x1 or x3. So here x2 is independent. So x2 is not varying with respect to change in input. Okay, so then the model is uncontrollable. So here y is connected. So output is connected well, all state variables. So the model is observable. So here, so any one of the state variable, if I change any one of them, output is going to change, so it is observable. Okay, that means, say for example, if I don't have x2 here, then I would say it is not observable either. Okay, here another example. So x1 dot equal to x2, x2 dot equal to minus 2x1 minus 3x2 plus u. So here x2 dot definitely is depending upon the input. Now x2 dot depending upon the input, at the same time it is also depending upon x2. Now if input changes, this is going to change, that might affect x2 also. So here you cannot tell whether the model is controllable or not, because there is indirect dependency. That indirect dependency, we don't know how much indirect dependency is there, so we cannot define that. There is another method we can find out. So here also y is also affected indirectly by x2, so the model could be observable, could be, we don't know. Okay, so how do you find the controllability test and observability test? So the controllability test is, it depends only on AB matrices. So x dot equal to ax plus bu, that's a state equation. Y equal to cx plus du. Okay, plus du. So the controllability is depends upon only AB matrix. So to construct a controllability matrix, PC, that's a PC, C indicates controllability. I'm representing that matrix matrix as P. So PC equal to B, AB, A square B, A cube B, etc., to the A to the power of n minus 1 times B. PC is always a square matrix. The model is controllable if PC is non-singular. That means determinant of PC is not equal to 0. Then we can say that model is controllable. That's about the controllability. When it comes to the observability depends upon AC matrices. So construct the observability matrix P naught. 0 indicates the P0 indicates the observability. C, CA, CA square, etc., up to the power C times a to the power of n minus 1. So P naught size is n by n. The model is observable if P naught is a singular. Determinant of P naught must not equal to 0. That's what it indicates. Okay, here is the first example. So I give you mathematical equation here. Find the given model in controllable is controllable or not. Also find the given model is observable or not. So here is the example: y double dot plus 3y dot plus 2y equal to u dot plus u. Whenever you, here find out this model or the system is controllable or not. So now what I'm going to do, I'm going to find the state equation, output equation by using first model is controllable canonical form. So I use the controllable canonical form. I draw the simulation diagram. Okay, how to do the controllable canonical form? Please watch my controllable canonical form videos. So by using controllable canonical form, I end up with x dot equal to x2, x1 dot equal to x2, x2 dot equal to minus 3x2 minus 2x1 plus u, y equal to x1 plus x2. Okay, so this is a controllable canonical form. So based on this, I found a equal to 0, 1, minus 3, minus 2, b equal to 0, 1. So if it is controllable or not, you will find out by using AB matrices. So first write down B, PC, B equal to 0, 1. AB, I found that is 1 minus 3. So I found that PC equal to 0, 1, 1 minus 3. Determinant of PC is not equal to 0. So the model is controllable. So one important point, whenever you solve a system or a mathematical equation by using controllable canonical form, definitely that model is going to be controllable. Okay, so that's what I want to prove here. Now P naught observability. So we're going to do the observability. So CA, I found CA equal to minus 2 minus 2. So determinant of P naught equal to 0. So this model is not observable, but sometimes it might be observable. So controllability, if we solve a problem by using controllable canonical form, definitely it is controllable, but we don't know whether it is observable or not. In this example, in this particular example, it ended up with it is not observable. So here is the same example. I solved it by using observable canonical form. It's the same equation: y double dot plus 3y dot plus 2y equal to u dot plus u. So just verification purpose. So y double dot plus 3y dot plus 2y equal to u dot plus u. It is the same example. Now I'm solving this by using observable canonical form. So find the state equation, output equation by using observable canonical form. Y double dot plus 3y dot plus 2y equal to u dot plus u. So integrate it twice, you end up with this is the simulation diagram. Please watch observable canonical form videos if you have questions how to solve this, how to find this. So the connection cannot be determined by inspection unless A is diagonal with non-repeated poles. We'll talk about it when we go to the Jordan form. But here it is. I end up with x1 dot equal to minus 3x1 plus x2 plus u, x2 dot equal to minus 2x1 plus u, y equal to x1. That's my output. There is no D in this case. So x dot, I found A matrix, B matrix and C. So first we will find PC. B times AB. B is 1, 1. AB, I found out minus 2, minus 2. So determinant of PC equal to 0. So the model is uncontrollable. See, it's the same example, but I used observable canonical form. In this method, I end up with the model is not controllable. Now, observability, P naught equal to C, CA. So 1, 0, minus 3, 1. So CA equal to minus 3, 1. Okay, CA must be, so CA's size is 1, 0, 1, 0. Those are the elements. The size of the CA is 1 by 2. A is 2 by 2, so it must be 1 by 2. I don't know why I put in this manner, minus 3, 1. Okay, but I used it in right format here. So C is 1, 0, CA is minus 3 and 1. So determinant of P naught is not equal to 0, so the model is observable in this case. Now, I'm going to solve the same thing by using Jordan form. Jordan form, same example. So here you have pole 0 cancellation. Never ever cancel the pole 0, because then the order of the system is going to change. Then it's not the given physical system to you. Okay, because at the same time we're not taking out any physical element. So we're not removing any physical element from that physical system. If you cancel out pole 0, that's what it indicates. Okay, so by Jordan form, I end up with ABC matrices. So from there, I found PC, determinant of PC is not equal to 0, so model is controllable. P naught, so here determinant of P naught is 0, so the model is unobservable. Now, I'm going to do the same thing. What we can do, so when you build the Jordan form, what you can do, you can move this 1, 0 elements over here, right? It's up to you where do you keep this C matrix, either here or here. Then if we change these elements over here, it might be observable, might not be controllable. Okay, so need not to be every model, need not to be need not to be controllable or observable, or need not to satisfy both, or need not to satisfy any one of those two. It could be satisfying both, it could be satisfying any one of those. Okay, now, so from this, the conclusion is, so for this particular system, I'm talking about for this particular system. For the given system, each model is either uncontrollable or unobservable. In this problem, we have a pole 0 cancellation. In general, if the transfer function of a system has pole 0 cancellation, then each model of the system will be either uncontrollable or unobservable. So if there is a pole 0 cancellation, then there is a possibility either it could be either uncontrollable or it could be either unobservable. H of S describes the system and it does not describe a specific model. If we test a model and find it uncontrollable or unobservable, then H of S of the system must have a pole 0 cancellation. The controllable canonical form is always controllable, but it may or may not be observable. Similarly, observable canonical form is always observable, but it may or may not be controllable. The Jordan form could be either way depending upon our choice of B and C. As I mentioned, where do you keep those elements, either starting of the simulation diagram or end of the simulation diagram. Okay. So some other important points, we always know the controllable canonical form always have elements like this. So AB matrices, so all the elements are going to be right here, and these rows 1 and 1. B is always 0, 0, 1. So if you have 4 by 4, then your A equal to 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and something like this, A, B, C, D. Okay, so in controllable canonical form, that's the A matrix, and B matrix is always the last element is going to be 1. All other elements are going to be 0. So elements in C may be any value depending upon what we have on the right side of the differential equation. Non-determinant of PC is not equal to 0, so it's always controllable. When it comes to the observable canonical form, so the elements in the last row are going to shift into first column. Okay, and C is going to be 1, 0, 0. B can have any values and determinant of P not equal to 0. Okay, I'll stop this video here. Thank you. It's a long video, but I hope you understand, you have good knowledge about the controllability and observability. Thank you.